Hi, good evening, everyone. In this lecture video, I am interested in presenting information concerning with air standard cycles and internal combustion engines. This may be a 15-minute video wherein I will be telling the synoptic overview of air standard cycles and internal combustion engines. You all know that in engineering thermodynamics, you are clearly aware of the fundamentals, the rudimentary terms associated with engineering thermodynamics. But in applied thermodynamics, we will be learning the application aspects very comprehensively. To begin with, in air standard cycles, we will be learning or we will get closer acquaintance with 5 thermodynamic cycles, namely Carnot, Otto, diesel, dual combustion, and Stirling cycles. In air standard cycles or gas power cycles, very professionally referred, initially we should be aware of the relevance of thermodynamic cycles. Later, one should clearly state the salient assumptions before we take up thermal analysis. As said, in this lecture video, I will be telling the synoptic overview of air standard cycles followed by internal combustion engines. So, we will tell the information pertaining to the 5 prominent thermodynamic cycles. To begin with, Carnot cycle. This is taken as a reference cycle wherein we will get to know the information pertaining to thermodynamic processes encumbered. In a Carnot cycle, we deal with 4 processes, 2 isentropics, 2 isothermal processes. Likewise, in Otto cycle, we deal with 4 thermodynamic processes, 2 isentropics, 2 constant volume processes. Analogously, in a diesel cycle, we deal with 2 isentropics, 2 other processes pertaining to constant pressure and constant volume processes. Next, penultimately, in a dual combustion cycle, we have 5 processes. Why? Because that is the amalgamation of Otto and diesel cycles. Finally, Stirling or regenerative cycle, that is the only cycle wherein isentropics are avoided. 2 isothermals, 2 constant volume processes. So friends, before we learn thermal analysis of all standard air power cycles or gas power cycles, we should be aware of how many processes are incorporated in every thermodynamic cycle. Then we will definitely get the idea how we can embark on the expressions for thermal efficiency and mean effective pressure. For all gas power cycles, it is highly inevitable to take up the derivations for thermal efficiency and mean effective pressure. But doing the derivation is not a big issue. The fundamental concept one should be aware is the terms associated, namely thermal efficiency and mean effective pressure. Thermal efficiency, it is defined as the ratio of work done to heat supplied. Usually work done is the difference between heat added and heat rejected. Whereas mean effective pressure or average pressure exerted on the piston is the ratio of work done to theoretical swept volume. Bearing this information in mind, undoubtedly we can take up the derivations for 5 standard cycles. But before you take up the derivation in a very elaborative manner, you should be aware of two prominent relations. Whatever the students or any faculty might have been well acquainted by learning first law of thermodynamics and engineering thermodynamics, they are two: temperature volume relation and pressure volume relation. Temperature volume relation, for example, you take up process 1 2, T2 by T1 equal to V1 by V2 to the power of gamma minus 1. Likewise, pressure volume relation P2 by P1 equal to V1 by V2 to the power of gamma. What is that V1 by V2? Why we need to take up those two relations? V1 by V2 depicts ratio of compression. So throughout the analysis of heat engines, a prominent parameter that helps in evaluating thermal efficiency is unquestionably compression ratio. If you know these things, no doubt you can take up the derivation for thermal efficiency and mean effective pressure for 5 cycles. What are those? Carnot, Otto, diesel, dual combustion, and lastly Stirling cycles. Carnot and Stirling, they are treated as the reference cycles. Before the conceive of Carnot cycle, Stirling cycle came to picture. In 1815, a Scottish minister, Sir Robert Stirling, conceived the first ever engine which is named after him in 1815, remember. But in 1824, Nicolas Leonard Sade Carnot, a French scientist come engineer, he conceived the idea of an engine which is named after him, Carnot cycle or Carnot engine. But three practically based engines what we need to learn are Otto, diesel and dual combustion cycles. If you get to know these information very comprehensively, solving numerical problems will not at all be a big difficulty. This is the synoptic overview concerning with air standard cycles. If a student or a faculty member has to get pertinent information pertaining to air standard cycles or gas power cycles, they should know these. In a minute I will run through. Initially, one should be clearly aware of the definition of thermodynamic cycle. Next, the salient assumptions to be made. Finally, thermal analysis of 5 air standard cycles. Then lastly, after touching the illustrative problems on gas power cycles or air standard cycles, we will make a comparison between these cycles, particularly Otto, diesel and dual cycles. If you bear these information in mind, then undoubtedly learning air standard cycles will be cakewalk for us. Now, the other segment which is very closely connected with air standard cycles is internal combustion engines. Normally, in any private institution or in any premier institution like IIT or NIT or any other top class foreign university having a very great name or reputation, no doubt they will combine air standard cycles with internal combustion engines. Why? Because both are interconnected. What unique information you can learn in internal combustion engines? In the elements of mechanical engineering, he or she will be well aware of the fundamentals of internal combustion engines. The definition of an engine, the distinction between internal combustion engine and external combustion engine, the broad classification, then the principle of operation of 4-stroke petrol engine followed by diesel engine, comparison between the two, and advantages and disadvantages. This is purely elementary level in knowing internal combustion engines. But when we need to learn engineering thermodynamics, particularly dealing with application of thermodynamics, he or she should be well accustomed with something called performance assessment. After knowing the theoretical detail like classification, the concept of detonation, then names of few alternate fuels very prominently used. Next, advantages and disadvantages of engines, very prominently combustion phenomenon in the case of spark ignition and compression ignition engines. These are all the theoretical detail what one should be clearly aware. But when we come to the analytical idea, one should be clearly aware of heat balance sheet. Normally in industries or in the laboratories, we will deal with heat balance sheet. Let me give a simple analogy. Normally, during the end of March, every year, irrespective of any nation, auditing is very common. The term auditing normally refers to the profitability or loss gained by a company, organization, or institute. Likewise, we does energy auditing. Energy savings or losses have been incurred or not, that we study. Very analogously, in the study of internal combustion engines, we deal with heat balance sheet. We will analyze the magnitude of heat losses. That is a very prominent thermodynamic cum mathematical tool effectively implemented to analyze some of the parameters dealing ultimately leading to the calculation of heat losses. Other than this, we learn four methods to determine total indicated power or frictional power. Before this, in the introductory concept, we will be well aware of the terms associated with internal combustion engines. Analytically, we have to be strong. If the course is purely theory based, then we should be aware of the mechanism. But we are dealing with engineering thermodynamics, purely a course of mathematical by nature or analytical reasoning is highly indispensable. For that, which are all the terms associated with internal combustion engines? Indicated power, friction power, brake power. Three values of power you should be aware of. Next, efficiency, thermal efficiency, mechanical efficiency, brake thermal efficiency, indicated thermal efficiency, then volumetric efficiency, brake specific fuel consumption, indicated and brake mean effective pressure, mechanical efficiency, scavenging efficiency, like that. So, dealing or studying these terms, no doubt we can solve any problem in the case of internal combustion engine. After getting acquainted with these terms, eventually, as said just now, we deal with four methods to evaluate total indicated power. The first, the most celebrated method is Morse test. Next, Williams line method. Third one, motoring test. Lastly, retardation test. If we are well aware of these ideas, learning internal combustion engines shall be very easy. Normally, internal combustion engines in the higher semesters or in the higher level of engineering or some other technical degree or technical education system, there is a separate elective for internal combustion engines. In the MTech or MS level, the students will be privileged to learn advanced internal combustion engines. Their level is absolutely appreciative. That is why normally in the first module of engineering thermodynamics or applied thermodynamics, what we professionally call, gas power cycles will be amalgamated with internal combustion engines. Why? Because both deal with the study of heat engines. This is what I was very much keen to give the information dealing with the synoptic overview of these modules. So in future also in every lecture video, I will be covering the synoptic or the epigrammatic overview of every module, what you need to study, what analytical ideas you have to learn, then learning engineering thermodynamics will be highly enjoyable. Thank you very much. Good luck.